These lectures cover the history of computers. The first generation of computers used vacuum tubes for digital logic elements and memory. A number of research and then commercial computers were built using vacuum tubes. For our purposes, it will be instructive to examine perhaps the most famous first generation computers, which is known as the IAS computers. Now, the fundamental design approach first was implemented in IAS computer is known as the store program concept. Now, this idea is attributed to John von Neumann, which we later call the von Neumann model. So, and also Alan Turing developed the idea at about the same time also. Now, the first publication of the idea was in 1945, which was proposed by von Neumann for a new computer, the EDVAC, which is the electronic discrete variable computer. Then in 1946, von Neumann and his colleagues began the design of a new store program computers, which referred to as the IAS computers at the Princeton Institute for Advanced Studies. The IAS computer, although not completed until 1952, became the prototype of all subsequent general purpose, again, computers. Now, this diagram shows the general structure of IAS computer. Now, it consists of a main memory, which store both the data and instructions, and also we have the arithmetic logic unit. So, arithmetic logic unit, which is capable of operating on binary data. Later, the arithmetic logic unit is part of the central processing unit or the processor. And it's the main unit that does the most of the arithmetic operations and logical decision making. Most computer tasks is based on arithmetic operations and logical decisions, true, false, etc. Also in the diagram here, we can see the control unit. Control unit which also interprets the instructions in memory and also causes them to be executed. Then we have the input and output module, or the input and output equipment, which is normally operated by the control unit. Now, this structure was outlined by von Neumann and later became, or as we said earlier, known as von Neumann model computer. So even our modern computers is based on this concept. Now, the first thing we should know is that since the device is primarily a computer, it will have to perform the elementary operations of arithmetic most frequently. So we have again addition, subtraction, multiplication, and division. So it's very reasonable that it should contain specialized organs for just these arithmetic operations. Also, it must observe, however, that while these principles as such is probably sound, the specific way in which it is realized will require a close scrutiny. Secondly, also, we may have the logical control of the device. So that is the proper sequence of its operation. Can be most efficiently carried out by the central control organ. Now, if the device is to be elastic, that is as near as possible all purpose, then the decision must be made between specific instruction given for and defining a particular program, and also the general control organs that say to it that these instructions, no matter what they are carried out. Now, thirdly, any device that is to carry out a long and complicated sequence of operation must have a considerable memory. So the diagram also here, we know that with a rare exception, all of the today's I would say all of today's computers have the same general structure and function. So again, as we said, they are referred to as von Neumann machines. It's also worthwhile at this point to describe briefly the operation of IAS computer. The terminology and also the notation for von Neumann are changed in the following conform more closely to modern usage. The examples accompanying this discussion are based on, again, on our course textbook. So a typical memory of IS computer will consist of somewhere around 4,096 storage location, which we call the words. Of the 40 binary digits or the bits each. Now, both data and instructions are stored there. So the numbers are represented in binary form, and each instruction is a binary code, as shown in this diagram. So this illustrates the format. Each number is represented by a signed bit and also a 39-bit value. A word may alternately contain, again, two 20 bits. Instructions, with each instruction consists of 8-bit operation code, which will be the opcode. Now, the control unit, again, operates the AIS by fetching instructions from memory and execute them one at a time. So again, we explain these operations with reference to the previous diagram. But first, we should know some few terms here. Now, most computers have different types of registers. So these are the general registers we may see in a computer. For example, the first one is the memory buffer registers, which we also call the MBR. Normally contains a word to be stored in memory or sent to the AIO unit, the input-output unit, or is used to receive a word from memory or from the IO unit. We also have the memory address register. So normally to specify the address in memory of the word to be written from or read into the MBR. We also have instruction register, which is IR, normally contains the 8-bit opcode instruction being executed. We also have instruction buffer register, which is normally employed to hold temporarily the right-hand instruction from a word in memory. We also have a special register, which we call the program counter. Program counter is very important. It always points to the next instruction that will be executed by the CPU. So this contains the address of the next instruction pair to be fetched from memory. Then we have accumulator AC and also multiplier quotient MQ. And normally this is employed to hold temporary operands and results of ALU operations. So for example, the result of multiply two 40-bit numbers is an 80-bit number. So the most significant 40-bit are stored in the AC or the accumulator. And the least significant is in the MQ or the multiplier quotient. So normally the IAS operates by repeatedly performing an instruction cycle, as we can see in the diagram given to us. So we can see we start an instruction. Is the next instruction in IBR? If no, then we have to go to the MAR and get a program pointer. If it's yet, then no memory access is required. Then we follow this step. So again, the IAS operates by repeatedly performing an instruction cycle as shown in the diagram. Now, each instruction cycle consists of two subcycles. So during the fetch cycle, the opcode of the next instruction is loaded into the IR. That's the instruction register. and the address portion is loaded into the MAR. Now, this instruction may be taken from the IBR, or it can be obtained from memory by loading a word into the MBR, and then down to the IBR, IR, and MAR. Why the indirection? Now, normally these operations are controlled by electronic circuit and result in the use of that data path. So to simplify the electronics, there's only one register that is used to specify the address in memory for a read or write, and only one register is used for the source and destination. Once the opcode is in the IR, the execute cycle is performed. Then the control secretary interpolates the opcode and execute the instruction by setting out the appropriate control signals to cause data to be moved or operation to be performed by the ALU. Now, the basic element of a digital computer, as we know, must perform storage, movement, processing, and control functions. And I think we went through this in an abstract level in our previous lectures. So only two fundamental types of components are required, as we can see in our diagram. We may have gates and memory cell. Now, a gate is a device that implements a simple Boolean or logical function. So again, we will cover this in the future, the logic gate, for example, AND gate, OR gate, etc., the operations. So for example, an AND gate with input of A and B and output of C will implement the expression if A and B are true, then C is true. Again, we will cover the concept of logic gates in the future. So such devices also are called gate because they control data flow in which the same way that a canal gates control the flow of water. The memory cell is a device that can store 1 bit of data. That is, the device can be in one of these two stable states at any time. By interconnecting large numbers of these fundamental devices, we can construct a computer. Again, the concept of logic gates, we may cover that in our future lessons or chapters. Also, we should understand the concept of integrated circuit. We know the vacuum tubes are very, very bad. They can easily bend, and they are very big, very heavy. So as the years go by, integrated circuit concept came up. So again, we can relate this to our 4 basic functions as following. We have the data storage provided by memory cells. We have the data processing provided by gates. And also we have data movement, which will be the path among the components that are used to move data from memory to memory, and also from memory through gates to memory. Then we have the control, which are the paths among the components can carry control signals. So let's say, for example, a gate will have 1 or 2 data input plus a control signal input that will activate the gate. Now, when the control signal is on, the gate performs its function on the data inputs and produce a data output. Now, when the control signal is off, the output line is null, such as is produced by a high impedance state. Similarly, also the memory cell will store the bit that is on its input lead when the right control signal is on, and also will place the bit that is in the cell on its output lead when the read control signal is on. Again, in the future, we may discuss more detail on gates, logic gates. So normally integrated circuits explore the fact that such components are transistors, resistors, and also conductors, can be fabricated from semiconductor, such as a silicon. So it's merely an extension of the solid state art to fabricate an entire circuit in a tiny piece of silicon rather than assemble discrete components made from separate pieces of silicon into the same circuit. So again, the fundamental building blocks of a digital circuit used to construct processors, memory, and other digital logic devices is the transistor. So the active part of a transistor is made of silicon and some other semiconductor materials that can, again, change its electrical state when pulsed. In its normal state, the material may be non-conductive or conductive, either impeding or allowing current flow. Now, when voltage is applied to the gate, the transistor changes its state. So a single self-contained transistor is what we call the discrete component. And this was used again throughout the 1950s and also the early 1960s. Electronic equipment was composed largely of discrete components, transistors, resistors, capacitors, and so on. And the discrete components were manufactured separately, packaged in their own containers, and soldered on or wired together onto, again, a Masonite-like circuit board, which we store in computers. So this is an example diagram. We can see one thing we should know that a microelectronic means literally is very, very small. That's a small electronics when we say microelectronics. Now, since the beginning of digital electronics and also computer industry, there has been a consistent trend toward the reduction in size of a digital electronic circuit. So the integrated, again, circuit explore the fact that such components as transistors, resistors, and conductors can be fabricated from a semiconductor such as silicon. So the diagram here again indicate what I would say a package processor or a memory chip will look like, shown as a package chip wired onto a motherboard. So this will be our close-up package chip and wired into a motherboard. Initially, only few gates or memory cells could be reliably manufactured and packaged together. These earlier integrated circuits are referred to as a small-scale integration or SSI. So we can see the growth in transistors count on integrated circuits from 1947 up to somewhere 2011. So which is over 10 billion from just only one in 1947. Here we have the first working transistors, then invention of integrated circuit in the 60s. Then Moore's law was promulgated in 1965. And we will discuss the concept about Moore's law. So I would say that this diagram will reflect the famous Moore's law, which again was propounded by Gordon Moore. And Gordon Moore was a co-founder. Was a co-founder of the Intel company. And the Intel company is one of the first companies to again develop processors. So Moore observed that the number of transistors that could be put in a single chip is going to be double every year. And collectively, I would say predicted that this again pace could continue into the near future. Now, to the surprise of many, including more, the pace continued year after year and decade after decade. So the pace showed to double every 18 months, and in 1970, but has sustained that rate ever since. Now, is it possible that Moore law will be like a log function? Because we know a log function may increase up to some stage, then it may stay constant throughout. So I don't know, most likely in the future, we may reach some stage that again, we cannot double or the rate will slow down. So that's the concept. 1965, Gordon Moore co-founded the Intel. Now, the cost of chip has remained virtually unchanged during this period of rapid growth in density. This means that the cost of computer logic and memory circuitry has fallen at a dramatic rate. An example would be that our first laptop, somewhere around 1992, was very heavy comparing to today's laptop. Back, we can remember the price was over $5,000. Today, we can even have a laptop for $200, which is even more powerful than early 1990 laptop. So because logic and also memory elements are placed together or very close together on more densely packed chips, the electrical path length is also shortened. And if the electrical path is shorted or becomes short, this means we are going to increase the operating speed of the computer. So again, the computer becomes smaller, making it more convenient to place in a different environment. Also, there's a reduction in power and the cooling requirements. Also, the interconnections on the IC are much more reliable than solder connections in the earlier 60s. So with more circuitry on each chip, there are few interchip connections also. So that's the consequences of Moore's law. The cost of computer logic, as we said, and memory circuitry has fallen at a dramatic state. Also, the electrical path length is shortening, increasing operating system, etc. So that's the diagram we have here. This will be a highlight of the evolution of the Intel product line from 8080, 8086, 80286, 80386, 804. And this leads us all the way to Pentium, to what we have today. So the world's first general purpose microprocessor, 8-bit machine, 8-bit data path to memory, was used in the first personal computer. The computer is Alta. Now, the more powerful 16-bit, that's why it's called 8086 machine, has instruction, cache, or queue that again prefetches the few instructions before they are executed. And this is the first appearance of the x86 architecture. So the 8088 was the variant of this processor and used in IBM first personal computers. Then we have the extension of 8086, which is 80286. This also addressing 16 megabyte memory instead of just 1 megabyte. Then we have 80386, Intel first 32-bit machine, first Intel processor to support multitasking. Then we introduced 80486 was introduced, use of bunch sophisticated and powerful cache technology, and also sophisticated instruction pipeline. Also refer a built-in math coprocessors. So we can say that again, the 80486 introduced the use of much more sophisticated and powerful cache technology, and also sophisticated instruction pipelining. And this 80486 also offered a built-in math coprocessor, also offloading complex math operations from the CPU or from the main CPU. Now we know Pentium came. With the Pentium, Intel introduced the use of superscalar techniques. That's para-programming concepts, simultaneous, which allow multiple instructions to execute in para. Also, Pentium Pro. The Pentium Pro, again, continued the move into superscalar organization, which began with the Pentium. Then we have Pentium 2, Pentium 3, Pentium 4, etc. Up to now. Till now, we are somewhere around Pentium 7 somewhere. Yeah. So again, we have Pentium Pro, which is continue the move into superscalar. Very important. This gives us the idea or enable us to do para-programming concept. Then, as we said, we have Pentium 2, 3, 4. Then also the core, first Intel x86 micro-core. Then core 2, extend the core architecture of 64 bits, etc. So that will be the conclusion of this lecture. In this lecture, again, we learn a few historical concepts. Here, in terms of computer architecture, we focus a lot on the performance of computers, mostly on the processors, the CPU. Now, this lecture is abstract level. In the future lectures, we're going to have a chapter again for memory, which will go detail. CPU will go more detail. So again, see you in the next lecture, and thank you for your time.